We begin with a brief review. Isaac Newton's shocking claim was that the same physics working here on Earth, that same physics that makes an apple fall, also makes a moon orbit. Well, that's a neat theory. So what's your proof? Well, Newton had something better than a proof. He had an explanation to a mystery, the mystery of Johannes Kepler, who, using a heliocentric solar system, found that planets do not play nice. They don't orbit in circles, and they don't keep constant speed. Why not? Because, said Newton, they're following these laws, Newton's laws, the same laws that work on Earth. So our challenge is to turn Isaac Newton's laws into Kepler's laws, starting this time with Kepler's second law, the equal area law, which means that planets speed up when getting closer to the sun and slow down when getting farther away. And if you think that lines sweeping out equal areas means integration, you're right. In rectangular coordinates, a small area dA equals dx dy. In polar coordinates, the small area dA equals r dr d theta. If you keep r constant and you integrate r from 0 to r and theta from 0 to 2 pi, you know what you get? You get the area of a circle, pi r squared. For an ellipse, area equals pi a b. Again, we will resist the urge to prove this, but you'll need it in part 3. Note that an ellipse will become a circle if a equals b equals r. Again, that's law 3. This is law 2, and this is our key thing to prove. Notice how wonderfully general it is. If 1/2 r squared d theta dt is constant, then the area swept out by the planet is constant in time. So let's do it. But first, we need to switch from polar coordinates to cylindrical coordinates, which are pretty darn similar, but in 3 dimensions. Why 3 dimensions? Because of our old friend h. H is a cross product, and cross products need 3 dimensions. Hold on. This is how we find r. But what about v? Can we find an expression for v? This takes some calculus. Calculus with trigonometric functions, which does not scare us one bit. Now, h, cross product, your time has come. But first, I cheated. See this derivative? I'm cheating. I'm sorry. I'm treating r as a constant. True for a circle, not true for an ellipse. And we should be using the product rule again. See that Vx term? It should have not just an r negative sign d theta dt, but also a dr dt cosine theta term in it. So in case you think I'm just trying to fill the screen with as many letters as possible, I'm leaving these out. The extra terms will all cancel out in the next step anyway. You could say we're operating under such a small window that r stays essentially constant. That's cheating. Check it out for yourself. If you don't believe me, they cancel out in the next step anyway. Okay, like we said, h, cross product, your time has come. And we said before that we expect h to be in the positive z direction, which is true from this formula. You see the x and y components are annihilated, so we focus on the z direction. Bada bing, bada boom, bada bang. And a bit of help from a trig identity to clean up the mess. We get a new expression for our old friend h. Looking good, 'cause we're done. Our goal was to show that 1/2 r squared d theta dt does not change in time. Well, if there's one thing we know about h, it's that h does not change in time. So we've proved second law. And we have a new non-obvious a new secret weapon, private purple, to use in the third proof. Meanwhile, the planets will be speeding up and slowing down, and we have one more to go. Kepler's third law, farther out, planets travel slower. Or more specifically, the orbital period squared is proportional to the cube of the planet's semi-major axis, which isn't exactly what this slide says, but luckily for us, the semi-major axis, in this case A, is equal to the average distance from the ellipse to the focal point. Again, it's a fun fact about ellipses, which we are resisting the urges to prove in this video. So let's make things easy, getting warmed up by proving Kepler's third law for a circular orbit. This makes things quite nice. We have Newton's second law. We have centripetal acceleration, v squared divided by r. Velocity is distance divided by time for one complete orbit. Distance is 2 pi r, that's the circumference. Time is period, capital T. So we have a nice equation for force. And hey, force, I know force is gravity. Substitute. Rearrange. Rearrange. And done. We have a new expression for Kepler's constant of proportionality too. Of course, Newton didn't have a value for big G, so we're not really that much better off. Anyway, we're done. For a circle. How about for an ellipse? We have equations for ellipses and more fun facts to avoid proving. And an old friend, Team Green, back from the first law. Let's put these guys to work, and this should not take long. We're almost done. Agreed? Okay, let's do it. Combined, substituted, rearranged, memorable. Not quite a secret weapon, not quite box-worthy, but you will see this guy. Again, speaking of secret weapons, here's Private Purple again, and her friend, the area of an ellipse, and the fact that H is constant in time, still constant in time. And with all this, we have a new expression for period, one that we can put immediately to work by squaring it, and remembering that equation for b squared, and substituting, and simplifying, and taking a bow. Because we're done, really done this time.